So good morning, everybody, and special thank you to NCI Data Science Learning Exchange for having promoted this initiative. The mortality tracking tool I'll be showing you today is something that we developed in a very short amount of time. And so the paper is not out if you're curious about that. Other papers are out and I'll mention them. And we are now entering a new communication model that is accelerated at all levels in software development as much as it is in communicating to our peers. So this is the page where most likely you got to from the announcement. If you click on the link, you go straight to the presentation. Sorry, you go straight to the tool. So the tool will assemble the data from its sources automatically. And this is where I'll spend the first part of the talk. I also have, so again, this is in the interest of speeding things up and shortening the distance between the producers and consumers of data science. So there's also Google Docs document that is open for commenting during this presentation. I'll close it then for view later. And I just put the link on the chat box of WebEx so you can get to it. So as I move through the presentation, please feel welcome to both ask questions in the chat box or to and I see quite a few people coming in, or to write them as comments to specific parts of the presentation. The first thing I need to say is that this is being recorded, and these slide notes, of course, will be made public at CBIT's GitHub site, the same place where you find the learning material. The tool I'll be presenting today has some characteristics that are, I think, novel, and that's very much part of the conversation. One of them being the nature of the team that developed it. So you have them here with links to each person's page. And you see it includes 2 branch chiefs, includes a number of senior investigators, but also software engineers and data engineers. The initiative itself is taking place within the data science group, although as you can say, saying within doesn't make sense anymore. This is really crossing different groups as it developed. And this was done in a way that is very open. So before I show the tool, I'd like to tell a few things about the environment where the tool emerged and how it works. So one thing you may find unusual is that not only the code is available, so this goes straight to GitHub. So the code is here, and when the code is being written by whom, there's full attribution. Also, issues are open, so if anyone has any issues, you can just go straight there and start writing your own issues, and we'll see, of course. Then we have this idea of using littered programming environments. So these are notebooks in the spirit of Jupyter notebooks, but they use a different technology. They live on the web, and they produce something called littered programming. They are fully portable. Anyone with a web browser can run them with no dependency on a server side, as would be the case of Jupyter. And finally, this may be the most startling feature, but I'm getting some background noise. Okay, this must be maybe the most startling part of the tool is that its development, in addition to responding to version control tools, also responds to social networking tools. So in this case, this is a Gitter. So it's a chat box. It's a tool associated with GitHub. And you see that it's a very open communication. Problems are stated, informal and formal comments are made, changes are added, and so on. And what you see in this environment is that the whole real estate of this user interface kind of contains the collaboration. You see here the changes in the code are happening on the site, and people can see them as they move. So now you get an idea that we are going from a group of people that is very diverse. You have the same list in the tool itself. And it's happening in an environment that is very interactive. So the first part of my presentation is going to be just to demonstrate the tool. My guess is that maybe half of you just want to use the tool. I would encourage you to be a little patient at the end of the demonstration and maybe endure a little bit of the techie jargon afterwards, because I'd like to get into this idea of data commons, what they are presently or what we want them to be presently, and what they are becoming, maybe without our desire to go in this direction. So there's some unintentional developments of data commons that I think are quite exciting. Talking about Gitter, in the notifications. See, so we are constantly connected, mostly not by email. So, but back to the flow. So first we'll have a 15-minute demonstration of the tool. Then we'll start touching on issues of architecture, but also issues of economy. How do people trade? So this is the data commons era. How do people trade in data assets? How different institutions compete to make these assets available to others? And how data services find a market in these new technological platforms like cloud computing and increasingly also edge computing. Okay, so you see the outline of the presentation, and I see quite a few of you are already in. So let's start with the tool then. So this is the full URL of the tool. The one below is a shortcut. And you'll notice that it's being served from GitHub. So as we change the code is served directly. And I see quite a few people clicking on it. So here we go. Again, I'm opening the tool yet again. And you see it's open now in many, many windows. So I'm going to start closing windows, which means that this is being delivered in an environment that is fully portable. So a few minutes about the tool itself. If I miss anything important, please write in the chat box. I have it open right next to me. So what you see here, that's the default, is that we are going to both CDC and John Hopkins COVID datasets. So they are both here, all with links, so you can open and find out what is going on in this other place. And so this is going straight to CDC. This is the paper as it came out. And you'll see that we are all embedded in an environment where GitHub socializes the coding exercise. So what CDC provides us as cause of death is this number of changes. The last one being new, of course, and having evolving codification standards. And this idea that we have to capture a data source that is evolving as we do it is very much part of what we're trying to do here. So let's look at the plot itself a little bit. So you see the data from the last 5 years. This is a standard in epidemiology to use the last 5 years as, say, as an internal standard for changes in the present year. And you see, for instance, that for all causes of death, so this is total mortality, you see that it changes between years. 2018, there was probably a bad flu season here, and 2015, full 5 years. Then in gray, you have the distance between the maximum and the minimum, and in black, you have the average of those 5 years. So anything in 2020 that is above or below the black line represents a deviation from an expectation. And so the graphic display of the data, and you'll see we can explore many different displays of the data, and what we do and other people do as well, as you'll see from the links. If you go below, there is a second plot that lists all the causes of death with a short note here. And if you want to know what are the ICD codes and the exact definition of the parameters, they are here. So the full definition is quite long, and they include these codes that wouldn't fit well in the legend. So we have a short note description of what the causes are. And indeed, you see COVID coming up here, and you see some things changing. So this is the point where we can start using the tool to explore variability, both between comorbidities and geographic locations. For instance, we could say, well, heart disease appears to be a problem as well and appears to have some correlation. So we could go check this out. So disease of the heart, we have the codes here. And you see, in fact, that is the case. The tool now gives you a number of features to explore these numbers. For instance, you could say, I'd like to see the mortality per 100,000. You see that we get the population as well. This is for all states. So now you just got the same numbers as the weekly mortality per 100,000. You may want to explore specific states, for instance, Maryland. And let's go back to all causes. And at this point, you could say, oh, that's interesting. How does this correlate with COVID? So now I take a pause to introduce one of the key architectural challenges of these tools. CDC and many data sources have been accelerated in their move towards this idea of real-time data commons. And so CDC, like many other data sources, is now providing data, I would say, not in real time in the sense that it's to the second, but real time in the sense that as it becomes available to them. And so you see this here, that some of the points, we leave them unconnected because this is counting in progress. We know that for the previous 3 weeks, CDC will be accumulating data, and over time, even values of older points will be corrected as CDC gets these values recounted. So this is an important feature that the tool is constantly changed. Now I could say, well, that's not the case for places where things can move faster. For instance, for COVID, Johns Hopkins University has a reference repository, as I think everybody knows. And so we could now compare the two and find out, for instance, for Maryland, where is CDC and where is the record that is available to the day. So this one, June 23rd, I believe that's yesterday. Yeah, today's 24th. So every 24 hours, Johns Hopkins updates these records. And so this is the distance between what is known for some parameters and what we take as reference data for causes of death. So let's hope I don't forget anything. So I'm going to go back to, for instance, all data, all causes, or maybe even disease of the heart, for instance. Let's say that you want to investigate the changes in 5 years, but you don't want to see 2020. So if you click on the legend, this information is made available. You can also zoom in. So what I'm doing here is just highlighting the fact that these are interactive tools that in real time, you can play with them. So if you double click, you get 1 point, double click again, you get all, and then you can put things in and out. If you double click on the panel, you go back to the original plot, which you can also get here. You can also get data directly, just practicality, or one trace, or for all traces. So this idea of immediate interactivity is very important to these tools. The same thing here for the full data. You see here the Johns Hopkins data and the CDC data. So I think I didn't forget too many things. Oh, this one is important. So at any point you may want to extract. So if you go to the data sources, there is a lot of data, many thousands of points and many parameters. So if you want just to see a slice of the data set you're visualizing, you just would click here and get the averages. So at this point you say, well, I'm more interested in the counts, and that sort of request can be addressed fairly quickly. So it's being replotted, it's done, and the data source is updated. So you see here now we have the counts, the averages and the counts. All right, so let's see if there are any questions. Oh, very good question. Okay, someone is asking, what programming language did we use? So this is a very super important point. This sort of model is evolving in the browser. So this is written in pure JavaScript. Now, for those who come from C and would be disappointed to see JavaScript as the language emerging in these places, note that C is now can be made available directly in the browser through WebAssembly. So this is for the techie people in the audience. WebAssembly is opening the browser to many languages. I'm trying to startle you a little bit with the answer to this question by opening. So this is something you can do in your own browser. If you go to more tools, developer tools, this panel opens on the right-hand side. So this is the part I promise not to spend more than a few seconds at this point. I'll come back to this later. I don't want you to lose the epidemiologist. But the point here is that we have access to everything from the network information. For instance, if I reload the page, you see the calls coming through. You see the errors, and there are always errors. You'll see this in many other environments. You have information about performance. You also have the full stack. So relational databases, non-SQL databases, all these things exist in the modern browser. So when we orchestrate web APIs, that's what we call it. When we orchestrate web APIs in this environment, we are making use of what's called a full stack. So the full stack is now available in the modern web browser in a cell phone, for instance. So you can open and close this environment. We'll see me do this a little bit later. And the closing point, before I go back to the epidemiology, is that it used to be that the browser was a user interface. And then we found out that there was a full machine growing underneath. This is the opposite of what happened in environments like R or MATLAB, where it was just the opposite. We had a powerful, so we can do things here. We had a powerful command line interface. Then we got an IDE, a place where to write code and debug it, so we can put debug points. And then eventually we got a decent user interface. So the browser is evolving in the opposite direction, but achieving the same result, having a powerful computational environment under everybody's web browsers. Okay, let's go back to the tool to make sure I covered everything. So you know how to get the data, you know how to compare causes and states, you know how to bring COVID and find out how things change between different sources. We can look at the accuracy of the data. Let's see, touch this. Okay, I didn't touch this one. So because the data is coming in real time, there are going to be states where the records just don't make sense, the present records. And so these states, we know, they can be detected and they were removed from the records. If you want them back, let's pick some specific examples like Pennsylvania or North Carolina. You see that they don't show up here because if they did, the numbers would be unclear, it would be incomplete. So I'm going to include them. So it's replotting. And now let's look at the data, for instance, for North Carolina. You see immediately with COVID that something went wrong, that suddenly the counts go down. And if you look for everything, you see that we'd have to go much further back to find records that are updated. I have no idea why North Carolina is so far behind in the records. This is not an unusual problem. For instance, this one is more unusual, Pennsylvania. So everything looks good as far as COVID, but when you go to anything else, I'm going to put all causes, you find out that for some reason, records are missing in these 2 months. So what the interesting take-home message from these observations is that this is real data. And if we were unable to make these sorts of features available to the fingertips of the domain experts, so again, notice the range of users, then we would be unable to proceed. So the take-home lesson here is that data commons, especially when it has this real-time nature, is completely hopeless if we don't involve the domain experts in the act of wrangling the data. And that's where the existence of a Gitter chat box enables people that may not be comfortable submitting GitHub issues, but they are comfortable texting us in a sense. So they can use a text box and tell us there's a problem, I'd like to see it addressed, or I'd like to contribute to its resolutions. Let's see if you have any. Yes, many questions I see. Is it possible to stratify the results based on gender? Yes. So all those data are now available. Gender, age, ethnic group. And indeed, the purpose of this tool is to validate an approach to tracking mortality, a little bit like a stock market model. This was an idea of Amy Barrington. She's right at the top of your list of authors. There she is. And so the idea is that we have these models where we have diseases that have expected and predicted values. And the expectations may be missed if there are new stratifications. So that is very much the intent. The part I want to make clear is that this cannot be done, or this cannot be imagined by the data engineer or the data scientist without the domain user asking the exact questions you are asking. So one more question. Yes, indeed. Accuracy. The data sourcing is important because of course, the accuracy. So we trust CDC, and that's why CDC was the primary target. But sometimes we need speed, and then we'd go to Johns Hopkins. So this ability to collate multiple sources means that we can have them all. We are not constrained in the number of sources we get. Let's move away from Pennsylvania and get to some, for instance, Texas here. So one last exercise of how you look for causes that may be unusual. For instance, you see Texas had a very high mortality in 2018. You may say, well, I remember they had a bad flu season. And indeed, there it is. So these sorts of quick exercises are possible. I noticed I forgot one more thing, which is to calculate the additional mortality for you. So you could do it from the CSV files. You can also do them from here. I'm going to show for the entire country now, all states, all causes, and I'm going to remove the problematic states. And you see the tool reassembles itself and makes these calculations for you. Oops, let's pick all states. There it is. And now, additional mortality. So this blue line, blue shade, you see under what was observed in 2020 and what was observed in the past 5 years. So the distance to the average is now added and produces the number you'd expect, around 120,000 people. And again, just to remember that this can always be collated with something that is looking to the future. And you see this in both plots. So at this point, I stop the tool. Maybe let's see if there are a few questions I should answer now before moving to the technology and the data comments. So how about relationships between COVID-19 reported deaths and the number of confirmed cases? So I think I have an answer, and I'm not going to answer for, I think, a good reason is that I'm not the epidemiologist in the group. And because the tool is shared, you could, for instance, pick up, let's pick Alabama right here, for instance. You could pick a state and a condition. Let's pick, for instance, disease of the heart, for example. And the link here represents the plot. So you could now go, for instance, to Gitter and ask us that same question. I'll put the link here to make it easier. So if in the tool you go to Gitter, you could ask the same question to the team and have the answer provided by an epidemiologist rather than by the data scientist. Let's see if there is anything else I should touch before moving to data comments. Yeah, so I have a ton of epidemiology questions about stratification of the mortality data. And yes, all this data is available and these tools are being developed. Some of them you get them already here. For instance, there was a request just to see excess mortality calculated with none of the confusions of the tool I showed you. And you see that the same data sources can be rendered in many different ways. So now you have all states here. You can pick a specific state again and have just the cumulative values represented for you. Another example would be, maybe I want to see not just mortality, but the number of cases. This was another one. Again, it goes to the same sources. And now you see not just the states, but also the counties. So let's pick Maryland. Let's pick our county, Montgomery. And I'll start adding our counties, just as an example. Let's go a little bit north, Frederick. Oops. Maybe Baltimore, there it is. You know, we can look at the values. In this case, we have 7-day totals here, and we have the date. So this is the standard plot. We have the values going up, down, and hopefully not going back up again. You have the cumulative values in a log scale. So the final value is accumulated here. But you can also get these transformations that are provided in response to specific requests. For instance, as the testing changes, one would expect the number of cases to change in response to that. But the percentage of cases the number of cases as a percent of total will not change the same way, because as the testing changes, the percent change of the testing will go back to some sort of line that reflects reality. So there are ways to represent the data that take into account stratifications or deviations. So now we could compare which states have a decreasing number of cases. So, okay, so I'm going to move back to the technology. That's why I feel most comfortable. Yes, modeling. Yeah, I'll try to touch into that. So CDC also provides models and they provide APIs to the models. Indeed, yes. This is a very, very good comment. Thank you, Mark. Okay, so now I'm going to go back to the technology. Remember, a lot of the issues you have are issues that we need to know about them in an environment where we can act. The socialization of this environment, of this solution, is what makes it possible. This is not the first time we do a tool like this, but in a sense, the opportunity and the advantage of doing it in this way only became pressing with COVID. And I'll touch on some other work we've done before. I'll have some plots here, so you can try to reproduce them to make sure you are comfortable with the tool. And now I'm going to move to the technology. So those who come from epidemiology, be patient a little bit. I think you may find rewarding then the discussion about data comments. I'm using a disintermediated architecture. What does this mean exactly? It means that, I would say a long time ago, but really 10 years ago, 20 years ago maximum, we were in a world where the web was about having a server-side component render things to the client side. So these three gray areas you see here is the server. So someone is running these machines, is maintaining them. Hopefully, those functionalities are being exposed to the web, because if they're exposed to the web, we have a decoupled, not yet a disintermediated, but a decoupled architecture, meaning that what happens here can be consumed by many user interfaces. So this is a feature that where the web distinguishes itself from other environments. But in the beginning of this web computing story, we only had access to the browser as a place to render, to visualize things. We wouldn't be doing computation in the browser, and that has changed. And this is very much part of this move of computation from a centralized location into the edge. So edge environments, so environments that are not central to the cloud, but at its edge. That includes, for instance, wearable devices. And so we have now the opportunity to start pushing the computation to the edge. Why? Because there is a lot of computation available at the edge we can use at no cost to us. And these issues of cost for data commons, I think, is going to be maybe the most exciting part of this presentation. Is that there is a data economy emerging that we can either resist or enhance. But this is very much a conversation we should start with no preconceptions about where we are going to end up, but maybe with some preconceptions about routes we should not take. And I'm sure people actually, I saw some questions already touch on this issue, what we should and shouldn't do, even if we can. But back to history, so we started here rendering things on the client side. Then we start creating services where some of the data wrangling is happening in the browser, and you see this in interaction. When interaction in a graphic, for instance, in a newspaper, New York Times, Washington Post, USA Today, they all have these interactive graphics. When you're interacting with these graphics, you're going back and forth at this level now. So some computation just moved to the other side. So what we see happening now is that all the computation is being pushed somewhere else. So once the data becomes available, we just push it somewhere else. So this architecture has been tried in a number of places. I've tried in 2015 the first time, and then a second time in 2019. I'm happy to show both examples. This may be the most impressive example. So I'm going to click on this link. And I'm going to traverse the exit records of 20-some million New York patients from different hospitals over a period of many, many years. And then we can go here, look, say, for instance, for cancer. We get a lot. We could plot it. You've seen this already. Let's say you're interested in glioblastoma, for instance. And let's imagine you're only interested in Manhattan. And you're interested, say, in 2015. And you find out that Memorial Sloan Kettering sees the most patients. You want to know more about these patients. There it is Memorial. So now things become interesting. The data was always coming from a source we don't control. So, and it's not being assembled in an Excel environment. So notice how the data is now migrating from one environment to another, and analytical environments are being triggered as these things happen. For instance, I'm now moving it to Google Docs. And once it's in Google, Google starts AI, or at least statistics and machine learning side, to find signal from noise. You just said array, got it. So some analysis was made on the fly. And this, so the reason I'm showing this story is to explain what the disintermediation means. It means that you just disintermediated the data scientist, the biostatistician, and you're now looking at features, statistical features that these environments created. So for those doing data science and not distinguish data science from biostatistics, bioinformatics, is the software engineering component. So the software engineering as a conduit to deliver analytical results directly to the place where the data is being produced and consumed. So let me make sure I didn't forget anything important. I didn't touch on visualizations, but I don't think you'll be surprised to know that there are many possibilities here. Just showing one really quick from 2015. So we are not constrained to scatter plots. We can have maps, we can have time, size, color, we can have animations, and choose what diseases we care about. And so this idea of full interaction between a quantitative landscape and the graphic results the domain expert can feel is very much what drives the data science and software engineering exercise. Again, I cannot overemphasize this. We could not do any of this without epidemiologists holding our hands and asking for things. So, and the environment is fully open, encourage you to do the same. So we touched on disintermediation and decoupling on the fly. You have the PIT for those who came late. If you use this link, you get these notes with all the links. And now we are going to move a little bit into the architectural issues of the middle layer. So let me open this a little bit. Okay, so let's take a little time with the architecture. So when we go straight to the source, Then we have this very efficient computational environment in our browsers, including our cell phones, do all sorts of things. And you see already, or at least you suspect, that the issue of size is not as important as we thought actually some years ago. Why? Because if our environment is poorly resourced, environments that are better resourced expose the functionalities that would allow partial data to be available on the client side. And you really don't notice the difference. And this happens through, that's the basis of data commons, in this narrow middle, to use Bob Grossman's terminology, where APIs allow you, for instance, to traverse 20-something million records of patients for all sorts. So there's a lot of information on each of those patients. So the APIs allow you to engage the data source in ways that are less static than they used to be. But in the model on the right, what you're avoiding is owning the problem. You own the solution and you engage the domain, but you don't own the problem. So in a more classic environment, you'd have, and when I say more classic, it doesn't mean that it's not used. It's actually more the norm still than the exception. You use some middle layer, like ArcGIS would be an example, where that you use to wrangle your data into data products that then you push to the client side. So over the years, and that's where FAIR comes into place, so the findable, accessible, interoperable, and reusable set of principles for stewardship of scientific data. That's what's also behind data commons. So if this part is hosted by a middle layer, then the persistence of this middle layer will be the weak link in the availability of the analytical product. So what we see is increasingly these tools happening on the right-hand side and not on the left-hand side. Again, apologies for the epidemiologists that may not be interested in the technology, but trust me, this plays a big role, because after you publish the paper, after you change your jobs, you would expect your analytical tools to remain alive. And if they have too many dependencies, it just takes one of these dependencies for things to go haywire. I have an example from my own work. I think I put it later. I won't touch on it now. Now a little bit of the human part. So if we are moving to the right-hand side model, then the computation is happening in the place we want it, and there's someone else's electrical bill, right? So there are no costs associated with this. And one critique we often get, so let's get that critique out of the way, is that, are we worth our salaries? I mean, we are just using other people's data, and now even other people's computers. We are not doing anything, right? Between brackets, anything. So in the answer to that critique is that we are guilty, exactly guilty of that. But I would say that this is exactly what data commons is about, is the ability to do secondary data analysis with minimal costs and maximum scalability. The challenge we have with COVID that we didn't ask for, I mean, many of us, at least it's my case, I thought another 5 years would go by before this would be a requirement. Can we do this in real time with all the confusions of real time, changing data standards, recoding of things, records that are not fully counted? Because this requires us to push the data wrangling to the device. So this is the bit that is new. Now, other people are doing it, New York Times, for example. So I'm going to pick an example here. So many of you noticed this paper at the time it came out. It was widely circulated. So New York Times complained that the federal government was not doing its duty, and they were going to do it for the federal government. So notice the psychology of this conversation. It's quite interesting. So what they say, well, we'll do it ourselves. We talk to the counties directly, and we are going to put it on GitHub. Let's go there. There is GitHub. So now New York Times can probably brag to get the data earlier, a little bit like John Hopkins does. It's the same thing. They provide the data in GitHub and make it available as quick as possible. So notice the real-time constraint now changing the human dynamics of the process. Now we could go, for instance, to issues. I'm going to type my name or my GitHub username. And you find out that, well, really, we are all in the same ecosystem. So you see here my conversation with New York Times data scientists, and we are trading things. So this is one of the things I'd like to make it clear. And now those who tune out of the technology, please come back in, because this part is interesting to you. We are now trading things with no exchanges of money. So I offer something here, say, well, thank you for the data. I know we are a little bit behind, so I'm using your data now. Thank you for this. And I wrote a library to make your data available to people like me, so to data scientists that are working for the federal government or for academic settings. And they say, oh, that's awesome. So the language changes as well, but the exposure is maximal. These things are here months after or many weeks after they happen. And then there is a trade. So the person who's using the JavaScript library says, well, I think you may want to know about this. So now I'm going to another person's GitHub. This is a New York Times employee, but this repository is outside of his employer domain. So we truly have a social network or mechanism evolving for people writing data science and curating data assets. So back to the point I wanted to make here, we are trading things, and I'll get to the economics last. So how do others do it? So let's see how different it is. So if you go, for instance, to the national institutes, and I always forget the acronym, you find environmental health sciences. They have a wonderful dashboard. So like everybody else, we are now in a hurry to provide these tools in real time so people can make real decisions when they are most effective. But what you see, now you won't be startled when I open the computer behind the web browser. What you see here is that there is a lot of middle layer getting in the way. And again, if it ever sounds like I'm complaining about something, please don't see it that way. I have plenty of examples from my own work where I do this. So you see that the tool is slower and this ecosystem of things is being assembled. Actually, this is maybe a good opportunity to also show you that this is the norm everywhere. For instance, if I go to New York Times, you see an ecosystem of services. So this is this idea of an economy where data and services are being exchanged and exposed in a page, and we can see it. It's of the nature of the web that code cannot be hidden. So nothing is compiled here. You also see offers for jobs. See here, we are hiring. And you can find out why someone else is hiring people to create data assets that you yourself may be consuming at some point. Again, I'm using New York Times as an extreme example. We could be using Johns Hopkins COVID data. And you can find out that COVID is now driving a lot of hiring. So you could go here. And before you know it, you're back. See, there it is. It says your job description is to curate this data set. And we are back to the same place we were just 2 minutes ago. So hopefully I got you a little dizzy about the market that is emerging in this environment, sometimes with a middle layer, sometimes without it. So Johns Hopkins also creates its own dashboard, and the first temptation is always to create a middle layer, and you see it takes a little time. But the moment you go into the data itself, you find out that the middle layer disappears. So this is still slow, right? You're still waiting for something to show up. But if you then go to, someone asked about models, maps and trends, I think it's here. There's a place where you get models. For instance, I can see models here. Maybe this one will have models. So I could go here to the left and try to harvest some data. Let's organize this a little bit. For instance, I could look for big things. You see, the sizes are quite substantial. Then I'll be looking for JSON. So a type of, there it is. See JSON here. Could try to preview. I don't see any data. But see, this is how we go after each other's data. Let me be patient for a second. It is not yet. Okay, let's try it again. Looking at size, the most recent ones. Let's click on something to see if the data changes. See, nothing happens. The middle layer is gone, and everything is now happening on the client side. So no more data coming through. Still wanted to show you some of the data so you see its shape. So it's all going through ArcGIS. So we see the data is being hidden at this level. All right, before I lose you. So we're trying to show that things are migrating towards the right. So from this environment to this, we often start here because we are in a hurry, but when we need real time and persistence, we are pushed in this direction. So CDC is doing the same thing. You may be luckier here with use of the browser as an environment. So you see this environment where see the reaction now is real time. There is no waiting, no calling to the client side. And so here you'd say there is no middle layer. If I open the DevTools again, please be patient. Let's see if we can fish something interesting this time. Let's get some data. Oh, there it is. We are going to find something for sure here. There it is. This means that I could now go to another place and use the same data source. This is a silly one. For instance, cancer.gov. And in another environment, let's open it. We could fetch this data. Let's get the URL. So those who like command line environments know that you have one here. And I'm going to get the data. And there it is. So we are no longer at CDC, we are now at NCI, but the data sources can go from one place to the other. So I hope I convinced you here that we very much have a fluid market for assets and services emerging. So I have a number of more examples here. I encourage you to go through them. I see I'm talking too much, so I'm going to rush a little bit the last conversation. So the reference for a lot of what we do falls under this idea of data commons. Data commons is kind of the third wave of something that started by being storage in a central location, and then something that was known as the data lake. So an environment where there is data and there is the ability to run computational processes. And then the third part, which is where data commons is there, when these two components, the computation and the data assets, they are aware of each other. So if you look at a certain data asset, there are a number of quantitative analyses that can, or data wrangling exercises, so a number of computational processes that can be triggered. So this is a model where the data, in a sense, analyzes itself in response to actions from the users. In my imagination, I see this as when you throw a piece of bread into a pond, the little fish find the bread and eat it, and the big fish eat the small fish, and so on. So you see a chain of dependencies that is established in a way that is organic, that is not choreographed. So the data commons are supposed to enable this model. The simplest description of data commons I've seen was by Tony, so CBIT's director, where it says it's a no download zone. So if the data can flow from one environment to the other, there is no point in downloading it. In a sense, we're actually asking for trouble if we download it, because then we have to manage the versions, and we have to make sure later on someone can repeat this. So what is emerging? So let's see if I forgot anything. Of course, I shouldn't forget this. The iconic environment is genomic data commons. This is the place where the idea of data commons was put into action. So let's go to the data portal. And you see now what I'm doing on the right. I'm just making sure I see what is going on. And maybe I can not only look at the code, so there is the code. I can change the code. And I can also look at the network activity. So for instance, now I could go to projects, for example. We go to the end of the calls for projects. So what you see here is the market, if you want, in full action. And you see here lots of hatchings, just like you saw me do before. So lots of them. You see images and calls. All right, so this is hopefully a little bit clear how data commons enable these markets where we can steal each other, steal in the good sense, reuse each other's data, to use the R fair. So how does it scale across omics? This is where we have a big question mark. So this is an NCI conversation, but I'm sure it's not just NCI that is going through the same problem. When we have many, many data types put together, when we are going after a vision, then the feedback from the use of intermediate versions of that vision will inform the direction we are heading. This is a time to have opinions and use those opinions to come up with hypotheses and then test them. And you see here a representation inspired on Bob Grossman's narrow middle that decouples and eventually disintermediates the data from its analytics. So I'll leave the note here. Okay, so this is an important one. This one I didn't see coming, and it's completely something COVID is teaching us. So when we are in a hurry, the predictability of the APIs is more important than them being standard, because any delay in making the data available on account of the need to be a standard is a delay that we cannot afford. These delays quickly scale into weeks, months, sometimes even years. We can just not afford this. So having each research group come up with its own API structures will delay the process. And what happens is, because this is an open market for data, those like New York Times or John Hopkins that rush making data available to the public in a predictable way, they'll be used first. And eventually, when the standards emerge in the back end, these places where people are used to go for predictability in the interoperability models, these places will be consuming the standards, and most people will not even be available of the standards. So this is a hard lesson I think we are learning with COVID. It's something we should, I think, discuss and find out how important the predictability is for the reusability of things that are in real time. This, in many meetings that don't go as well as we hope, when people are trying to decide where are they going to share things, like causes of mortality, this is very much the model that pushes people away from sharing. Is don't force me into your walled garden because I've been cultivating my own. So our walled gardens, they need to be respected, and they need to be able to interoperate with this data commons environment. But forcing people into a shared computational environment has a very bad history, and one that is untenable with COVID. So again, because of the delay element. Time in the past was not a parameter in these conversations. Then I have an example. So if APIs are emerging in the web environment and they are orchestrating calls to the client side, what does this mean for the data economy I promised to touch on? So the data aggregation is happening in real time, it's distributed, and a number of things are happening. So as you saw from the mortality tracking, the data wrangling is happening somewhere, right? And this somewhere, we know now, has to be in the same place where everything else is happening. So if I go to the code, so you see that these are not just empty words. They mean many, many hours of work by the person writing the tools. So if I go down, you quickly see here, this is where the data is being called. You see here data.cdc.gov. Again, we are just using other people's data with a limit at 10,000 in only parameter. Then we acquire the data, and then we spend quite a few lines of code cleaning it. And you see this somewhere, I think it's even actually called cleaning. There it is, data track clean. So we're doing things like CDC noticed at some point that they should not have empty spaces, but underscores and their parameter names. And sometimes ICD codes change, there's nothing we can do about this. So there's a new one here. And so you see here, we are parsing one into the other. So these are typical data wrangling problems. It's very typical of data science in general. And we are now doing it on the client side. So none of this is happening on the server side. Otherwise, the scalability will be compromised. We're almost done here, and I know I'm almost out of time. So if we are advancing the monetized data assets, for example, how do we compete in the good sense to generate value? So of course, we've seen many examples of this model. Wikipedia, for instance, demonetizes assets that in the past required controlled access and for cost reasons to make it sustainable, and now it doesn't. Also, if some places move towards literal programming, like newspapers, media in general, we should do the same, I think. So I have an example here. This is just to make the point that there are lots of examples, and you're welcome to see them. All the links are open. You can compare things. And it's is this a newspaper? No, this is an NCI data scientist making its analytics available to others. How do people trade? So I wanted to show an example where I'm complaining about myself. So this paper just came out. It's about using AI to find lymphocytes in large images. And the question is, what is most likely to break here? And the answer is, it's this part on the right-hand side, because it's not going straight to the data. It's going to a place that is doing zoom in, zoom out of an image. And we hope this place will be there for a long time, but we don't know for how long. Whereas things that are represented here, they are coming straight from a place that is persistent, designed for persistence and version control. And we are almost at the last one. So some data points for what's going on around us. You see this in the last week's Economist. Only 10% of IT is in the cloud. So the IT is around a $4 trillion industry. 400 billion are in the cloud. But the expectation is that most of it will be there. So this gives us some pause. When we look at the NIH Strides program, it's amazing the door that Strides opens for data science. It's truly, in fact, hard to think how data science would advance at the same speed as the opportunities and needs without the Strides program. So we're really happy about that here. Now we also have this second data point, is that by 2023, this may be wrong, maybe 2024, but what we see is that most of cloud computing will happen at the edge. So I left some links here to explain why computation is, as it moves to your cell phones and to your web browsers, it's also moving to your sensors and maybe to your next generation sequencing facilities and so on. So a lot is happening in this space that will change this conversation quickly. Last note is make sure to provide us with some feedback. So the link is right here. It's a short questionnaire. It's only 1 page, 10 questions, and it will help NCI and understand what value you found here, what suggestions you have. So please, oh, very good. I see lots of people clicking on it. For those in the attendance from the Cloud for Bio hackathon, please know that you don't get the rest of the morning free. We'll go back to GoToMeeting in a few minutes. And I'll stop here, open for questions. Okay, I'm intrigued by the reference to Google AI. What sort of options are available for using these tools? Very good. So the cloud is evolving to becoming kind of a distributed desktop where we share things. So that's the governance component. On the service component, cloud providers try to automate, so the whole idea of disintermediation, things that we spend our entire careers knowing how to do. For instance, in the case of Google AI, Google AutoML automates the hyperparameterization of the deep learning models. So we can generate models by creating environments where domain experts like pathologists, in the example you saw of segmenting whole slide images, pathologists classify regions of interest, the AI is triggered, and the segmentation is updated on the basis of the hypothesis of the domain expert that a certain feature would be important. And so the data scientist provides the conduit for this interaction to go back and forth. The cloud AI service, in this case, AutoML, which we get through Strides. So again, thank you, Strides. It's what makes this available. Okay, fluid open access interoperable systems talking to each other. Sorry. How are the checks and balances in place to deter any hackers to manipulate these data systems? Very, very, very good. So being at NCI means we have people looking over our shoulders, and that's a huge value. We cannot overemphasize how important it is that we have services that are already FedRAMP and FISMA compliant. So this idea of oversight happens above us. Now, are we open to hacking? Yes, we are, and it does happen. Is this safer than the alternative of having an on-prem system that we think our best security person can handle? No, it's a lot safer to do it in the cloud, and there's plenty of data on this. What the cloud providers do is that they often take the liability of hacking, and so if solving those problems is a line item in their investment, and so they want to maximize the return on investment by knowing how to deter the hackers. Of course, if you are saying a computer science program at a place like Stanford, for instance, as you exit the program, Google, Facebook, and other companies will be hiring you. So these companies are actually hiring our best students, and this is the case for me. They are hiring our best students to provide security as a service. It's kind of a strange service, but that's exactly what's going on. And I think we just got out of time. Sorry about so many good questions here. We are going to use this as further for our own developments. And Lynn, I think I'll stop here in the interest of time.
Thank you, Jonas, and thank you, everyone. Jonas, if you and everyone have a few more minutes, it's up to you.
Yes, I sure do. So if you want to open the mic and let people ask questions directly, I'm happy to answer, Lynn. All right, we have lots of thank yous and people with meetings at 10:30. Completely understand.
One question, the presentation and recording of this presentation will be available on the Data Science Learning Exchange website. And we will also, I guess, we'll try to send an email to everyone with that link, but I think many of you have it.
Those who are looking at the Google Docs, you have them right at the beginning. I'm pretty sure I put it there. Yes, there it is.
There it is. So it will be posted within a few hours.
And same thing for the video. So you'll have the notes, the video, and the links, of course. I have a lot of questions. If you don't mind, I'll go back to a couple of them. For those of you asking about dying from COVID versus... Oh, okay. Yes, very good. That's a very good question. So CDC is very careful about this. Instead of just reporting deaths, they report two types of deaths. So the ones of COVID and with COVID, and they get different codes. Again, this is something I learned from the epidemiologists. I'm talking out of turn in a sense. So let's go to the tool. And so when you look for COVID, you see these two. So the green is with COVID and the red is of COVID. And when you open the file, you see that unlike the other causes of death, COVID has two columns, of COVID and with COVID. And if you go further down, you can find exact ICD new codes. I'm assuming it's ICD codes, so they are right here. If you go to the source data, remember everything we do is behave like, in a sense, vultures of other people's data. So you can always go here and get the raw data. So there's the resource, fully documented. So this idea of full traceability, full reusability is very important to us. And you can look at the data. Okay, more questions. Google AI already. Yeah, no modeling involved. Yeah, but so modeling generates points in graphs as well. I didn't get to that point, but quite a few of the CDC sources include predictions by a number of models. So this idea of disintermediation also means that the people we work with are no longer hostage of our analytical solutions. They can use other analytical solutions, other models, other predictions for the same data. So it really opens up things quite a bit. And Lynn, I think we stop here. Unless you see a question that is very pressing and you think I should address. There's one about modeling, actually. Do you take in consideration the racial, ethnic diversity and disparity in this model system? So remember, there are no models. We're not using models in this specific tool. Of course, we want to model these things, but that happens after the data. For those interested in this intermediation of data-rich environments and modeling-rich environments, there is a great paper called, where is it? The Unreasonable Effectiveness of Data. So this is a reference to an old paper, The Unreasonable Effectiveness of Mathematics. So highly recommend that discussion. The interesting point, and this is really where we are heading, is that when you have a lot of data, there is no reason not to let the data speak for itself, because the data is already populating enough of the domain of possibilities to inform your own hypothesis. So this is the idea of looking at the data before coming up with hypothesis. Sounds obvious, but it's not so obvious, because we often have a lot more data than we are willing to spend time looking at before we propose our hypothesis. And I'll stop here. Okay, back to you.
Thank you so much, Jonas, and everyone for participating.
All right, thank you.
Really appreciate it, and some great questions. Look forward to your feedback too, and the recording and presentation will be up soon. Later today.
Thank you for promoting this. Yeah, thank you. Bye-bye.
Thank you so much.